Great. Hey everyone. I hope all the projects have been going well and you guys have been having fun with the process. Um, Ken's going to be heavy on the talking today. He's doing the bulk of the education through fabrication. He's going to start with going through his work and then teach process of a toolpath and then explain two methods, extrusion and pick and place. But I just wanted to start with a quick talk on fabrication in the context of the real environment because when we're working on a biodesign project, as we've discussed before, it inherently is also a conversation on material development and new iterative design process. In the industry, you typically see these materials. Everyone's not surprised by what they see on the screen here. I mean, it's what's understood, it's what's expected when the new building is made. But through this new thinking, you start reconsidering the way that you can start developing and providing materials that are better for the environment and for the construction industry. These examples that I laid out here are just the beginning of many that have been working to make something just better and new. Um, I think Biomason is a very good example of an industrialized version of something. They have actually been selling their tiles made from bacteria, which is incredible. Bastian Bear is also on his way. He's been working a lot on these mineralized fibers and has exhibited some of his work over the last few years. There's also been these last two are just research from papers that I've read because I personally have been interested in compression strength. And so having just basic mixes of kind of raw ingredients, you can actually get pretty strong strengths and start hinting at the idea of can we provide more for the future. So in that context, like I always want you guys to think about how when you're working on this project and you're trying to develop a kind of a new system, there's just going to be like just some testing that would be beneficial to kind of prove your point or make yourself more kind of relevant in the industry. So you'll go through a series of iterations and composites, mixes, like mold testing. Everything that you think can go wrong will go wrong. And it's good to kind of work through it and understand this process and be aware of it because it's as expected when you kind of get focused and more interested in this kind of field. And by giving yourself credibility and doing formal testing, you'll kind of have an upper hand in this kind of new environment. So yeah, that was just a quick talk just to explain the context behind the reasoning for what, you know, we do and why Ken is going to explain this uh, process and fabrication. Take it away, Ken.
Cool. Thanks, man. Okay, so I'm gonna I'm gonna talk a little bit about the work that I did in the masters, and also I'm gonna introduce some concepts in terms of parametric modeling around toolpath production and a couple of scripts, one for extrusion and one for pick and place. Both are additive manufacturing methods, but I think they're useful. Well, to some of you guys, it might be useful for your project. It also might be useful to kind of understand how these computational tools can allow you to not only have a lot of control over the information, the environmental information that you can get from them, and also from the complexity of the geometries that you can produce, but they can also give you agency of the whole construction process. I think the democratization of these computational tools is the first step. The next step is gonna be like the democratization of the fabrication tools. I think architecture for a long time has been quite detached, not in all cases, but in many cases, from the actual construction fabrication process. We're starting to see 3D printers as a common thing in some architectural studios and practices. I think the next thing to become quite ubiquitous in these practices is going to be robotic arms, because they allow for a lot of possibilities in prototyping, in quick prototyping, and in many cases it can give you agency over a large-scale construction process that yeah, basically you can take your designs to reality with very little resources and manpower. So I'm going to start by showing you guys some of the work that I did in the masters, which was very much fabrication focused and fabrication informed, if that makes sense. I'm going to start by showing a video that a good friend of ours, Nicholas, took of the work that we did right after I finished the masters. Ed, can you guys see a video on my screen? Okay, I presume
You're
it
all
must be.
good, yeah.
Okay, cool. Yeah, so this project involved material design around a soil biopolymer-based material. And we had to design our units according to the purpose that we were trying to achieve. We were using a robotic arm, but the robot, the arm is just that, the arm. You have to design the hand of the arm yourself and build it for the purpose that you require. You have to, once you get to a geometrical idea of what you want to produce, in this case, these were like large-scale planters for a landscape intervention in a meanwhile set in London. You need to decide like which toolpath is the right one, which a lot of considerations from the reality of bringing these things to life end up affecting the design in a large manner. Ideally, we would have had the chance to print the structures on site, but because of logistical limitations, we ended up printing them at the university and then bringing them into the site. I'm gonna get in a little bit more into that later. But yeah, this is definitely not a building yet. These are like middle scale structures, but they are part of like an ongoing research. Yeah, I guess the message that I was trying to convey here is that this is a process, like it's an evolution of a thing. Okay, and I'm gonna, I guess, try to tell the story from the beginning here. So this is basically the work that I did in the masters around soil 3D printing. This was the Biointegrated Design program at the Bartlett, in which I met Edward and Dana as well. Yeah, so the work that I did in the masters initially revolved around the production of soil-based material that didn't have to be reinforced with cement, because in many cases in soil construction, they reinforce it with cement, and cement is quite pollutant, it's quite contaminant, it's a problem. So I started doing research into biopolymers. I found that biopolymers were an interesting material possibility, and I was very interested in the possibility of cross-linking some of these biopolymers to see if they could improve on my soil material. I started working with 3, well, more like 5 at the beginning, but I did a lot of testing on these 3 particular biopolymers, xanthan gum, sodium alginate, and kappa carrageenan. I ended up focusing more on the first 2, particularly xanthan gum. From a recommendation from one of our tutors as a fabrication method, I started exploring impact printing. In his perspective, it could be an interesting possibility to use with soil, because soil is quite heterogeneous. That's the main issue when we're talking about 3D printing. And when we talk about extrusion, you need a continuous flow of material. You need a material of a very particular viscosity. And soil isn't really great for that. It has very different particle sizes. So it gets stuck in the machine. It doesn't extrude at a continuous rate. So impact printing, it takes still hydrated units, but it takes individual units. They're not trying to extrude a continuous flow. And it presses them, it either shoots them or presses them in place when they're trying to build the geometry. So this very solid but still viscous material pushes against its neighbors and produces like a physical interlocking of the units, kind of like a midpoint between extrusion and bricklaying, so to say. You can see in this chart to the left, this is all a research that started at ETH in Zurich by this group of architects. The studio is called Gramation Kohler. And you can see they did extensive testing on material composition and how this interlocking provides much more stability for the structure. I did my own set of tests with all the biopolymers that I showed you guys. And we were looking for addition between the units. We were trying to get the units to stick together. That was our first purpose, to try to do this test before going to a robot. And in most cases, it didn't really work. But when we got to xanthan gum, in a particular recipe, so to say, in some very calibrated levels of concentration, we couldn't pull these units apart. And this was my colleague, Leticia Mochli, also from the program. She helped me with this test, and she couldn't pull these two pieces apart. And I tried it myself. I also couldn't. Like it was like kind of like a eureka moment. Okay, this is something useful. So we started testing with the robot. We were using a UR10 robot with a pneumatic end effector. This was designed and produced by previous students from our program, Guillaume Perrouzet and I can't remember the name of his colleague. They built this end effector. We call the robot cant end effector. And they built it for a previous project, and they discarded it quite quickly because it didn't fit their purpose, but it did serve mine. So I kind of inherited it, and we started collaborating with these students from this other master program called Design for Manufacturing that we're also trying to work on impact printing. And it's a quite simple end effector. It's just an acrylic tube with a pneumatic plunger. And the idea is that the acrylic tube could lift the unit just by the friction. The unit fit perfectly under the acrylic tube, so we had to calibrate a pickup plane quite precisely, and the unit would stay in place just by the friction against the walls of the acrylic tube. Then it would travel to the final position as if it were a worker placing a brick from a brick wall. And then the plunger would impact the unit into place. That way we would allocate the material one by one. The thing is, when a bricklayer wants to produce even a straight brick, it has to do it very mindfully. It has to take a lot of measurements and calculations. The robot is very dumb. It doesn't do anything by itself. You have to tell it how to do everything. And if you tell it to crash against itself, it will do it. So you have to, all of this each movement of the robot you have to program and calibrate yourself, and you have to do a lot of testing. But once everything's calibrated, the robot is incredibly precise. It can build like a straight wall or a curved wall or a bolt with high precision without the requirement of any additional measurements. So it has that advantage over a human builder, so to say. So each one of these targets and commands, as I was mentioning, has to be calibrated. We're going to go through this on the toolpath side of things. So this was kind of the beginning of me trying to build these soil structures with this new material in these quite complex geometries. That was kind of the goal, but I still kind of needed to tie this to a more an overarching project, a bigger architectural purpose. But this was just explorative. So I did a bit more research into the material that I was working with. These samples to the left are raw soil samples, and the samples to the right have the biopolymer added to them. So you can see how the polymer builds these web-like structures between the soil particles. So it does make it a much sturdier material. I eventually found some literature about how this xanthan gum enriched soil mixes could reach levels of mechanical compression properties similar to cement enriched soil. So it's quite an interesting alternative to the addition of cement in soil buildings while being completely non-contaminant and biodegradable. So it's a very interesting polymer. So I started using Grasshopper to kind of design these compressive structures. I found this plugin called Caramba, which helps you analyze structures and also helps you with these form finding algorithms. I did my first print by hand because the workshop was closed for maintenance. So this arm was my own. And I decided to use this adaptive formwork to try to get me to produce much more complex shapes. So I used this dry soil as like a formwork. So I would print, so to say, a layer, and I would fill soil around it, and then next layer, soil, layer, soil. So I was using soil as a material to build, but I was also using it as a support for the geometries that I was producing. Eventually, I got access to the robot again. So I printed this structure, this spiral, as an exploration of this, well, first of all, the end effector and also the adaptive formwork with the dry soil. So again, the robot would print a layer and I would fill, let me see if I can move this forward because it's going to get tedious. Oh no, that's just it. Okay. Not all of my prints were successful. This one collapsed. I made a mistake on the layer height and I left out many, or maybe a bit too many openings. At this point, I decided to start doing something that had kind of a direction. So I was interested in the production of self-shading walls. The concept of self-shading walls is that you produce walls that have a waving geometry that has the potential of projecting shade on themselves. This also increases the surface area that can help with heat transfer. So it's quite an interesting alternative in high solar radiation climates. And so this gave me the inspiration for the wavy pattern that I was trying to get. This was all done on Ladybug, this script that I shared with you guys yesterday. So those simulations are also within what you can do in your own computer. Yeah, I I printed this little guy that collapsed a few hours later. And after a few collapses, I started running these structural simulations on this other plugin that you can find in Grasshopper, quite useful, Caramba. And these simulations were telling me that there were stress points and that the structure was probably prone to collapse because it was leaning to one side. So I started to try to introduce the information that this script was giving me into the process. That's where I got to this half collapse. This was showing me quite a big area of stress on this side of the thing. And initially it was fine. Like I was taking out the support soil, and I thought that it was gonna, remain standing up, but it only happens for a second. I hope that you can see it, but by the end it starts to fall down, and one of my friends caught it. Yeah, so it fell down. Well, it didn't fell down completely. We put like a support in front of it, and we let it dry for like a week. And after a week, it just stood there. Like once the material had dried, even though it was like partially broken down and partially collapsed, it remained like leaning to the side, but still alive, so to say. So that was interesting because this was telling me that even though the material is ductile while it's still curing, once it cures, it's quite solid. So this was an interesting collapse. This sometimes even the unsuccessful results that you get can give you a lot of information. So this gave me a lot more faith in the material after it has had some time to cure, to dry, so to say. And yeah, again, the structural simulations were basically telling me what was about to happen. Is if you like see the most dramatic distortion of the morphology according to the simulation was going to happen on this fold almost midway through the height of the structure, and that's precisely what happened. That's the first thing that broke out. So these simulations ended up being more accurate than I had predicted. So this led me to the one that stood up, the boy that lived. We call this one the wavy wall. It was printed in the same way, layer by layer, filling dry soil after each layer to kind of support it while it cured. And also to play it safe, I took a lot more time to take out the support soil. I did it in a day and a half, allowing the soil that was newly exposed to dry out. And yeah, that one, the structural simulations were also quite conservative, very little deformation, very happy colors, a lot of blue. And yeah, that one survived, and it was super sturdy. It had this complex geometrical expression that I wanted to achieve, so I was quite happy with this one. But at this point, I guess I had proved that I could build something with this unit size, which was quite small, so it was kind of time to see how I could go big or bigger at least. And that's where we had to redesign the end effector. I initially tried to just get a larger tube, which kind of sounds stupid, but it was, I guess, the first step. Sometimes a stupid idea is better than no idea. So yeah, I tried the big tube approach. It didn't work because the bullet was way too heavy for this, just the friction from the tube to hold it in place. So that was a failure, but at least the start of an idea. I redesigned it with a second pneumatic plunger. The idea would be that this second pneumatic plunger would shoot into the material and keep it in place while the arm travels. That was the idea. So at this point, we had to produce our thesis project these projects in our program are collaborative. I was working with two colleagues from the masters, Itamar Lilienthal, who was focusing on environmental simulations, and Leticia Mohli, who was focusing on embedding soil with plant growth promoting bacteria. So we devised this idea of producing this building in Tijuana, that the soil building 3D printed, that could erode in a controlled manner. And we would have a section of the building for human purposes, so to say, that would have enough of a concentration of the biopolymer to not erode away. And we would have another section of the building to be temporary, to be erodible. And the idea was to inoculate these sections of the building, this material, this erodible material, with the bacteria that Leticia was working with, because the main erosion source would be moisture. So in the presence of moisture, this material would break down. It would release this bacteria that helps plants grow. And you have water, you have bacteria that allows these plants to absorb nutrients so you can get growth. And the idea was to repopulate, to regreen this environment that had been depleted of all vegetation through the decay of our building, through the erosion process of our building. So we designed this communal center in Tijuana, all around soil and soil 3D printing. My initial idea was to just build the walls with soil and to have like a regular wooden roof or something like that. But Marcos Cruz, our program director, he kind of decided to challenge me to do as much with soil as possible. He was like, hey, try to have the walls, the roof, everything that you can out of soil, try to make it soil, and whatever you can't, okay, bring in another material. So that was kind of the challenge. I tried to do it the best way I could. This was all designed in Grasshopper. Once you get the ball rolling, these scripts just happen. And Itamar helped us in Houdini to figure out the optimal position for the degradable material, for this material that could erode away. He also did a lot of work on environmental simulations, which were instrumental to control this erosion process and also to provide the inside of these buildings with enough comfort. And my challenge here was to produce a fabrication method that could allow for multi-material structural elements. So a 3D printed wall that could allow for two materials to coexist and to perform structurally. So yeah, I decided to control the degradability of the material through the percentage of polymer that the material had, because I knew that the polymer not only improved on the mechanical properties, but it also improved on the water resistance of the material. So if I could calibrate the amount of biopolymer on the bullet that I'm printing, then I can essentially control the way that a section of this building erodes or not. That was the hypothesis. So I separated the print targets in the toolpath into sections. The red targets were supposed to be material that had less biopolymer, more clay. This was the planning of the thing, and this was the idea of the predicted erosion process. And yeah, we printed it. This section separated to the right, I'm not sure if you can see it in your screens, but it has more of a reddish hue. That's because these bullets had more clay in the mix, and the bullets to the left had the biopolymer. Those were the bullets that were supposed to not erode away. And Leticia did a lot of testing, basically spraying water periodically on the wall, which is usually a no-no for earthen walls. but we had faith on the biopolymer and how it would perform. So we did a lot of thermography, so pictures with a thermal camera to see how the wall was absorbing the water, and it did as we predicted. The clay-based material started absorbing water. So that was quite interesting to see happening. And you can also see here how the bullets to the right are starting to dissolve and erode away, while the bullets to the left are like quite okay. So that was interesting to see. This is after drying. You can see the bullets again to the right, starting to break down. Bullets to the left, all good. Some of the bullets that we stored with the bacteria that Leticia had synthesized started growing moss and even this piece of grass. We hadn't planted anything on these bullets, so that was starting to prove that also the hypothesis that this bacteria could allow for stuff to grow and to thrive even in this soil material that's quite dense. It also kind of proved that the polymer that we were using is non-toxic because it also allowed for this thing to grow. So yeah, that was quite interesting to see. Yeah, that was our thesis project. And then the program directors asked me to help them with this landscape project in Barking Riverside, East London. This was the design. There were supposed to be large-scale planters to kind of test the bioremediation properties of the plants on the site, because this was supposed to be contaminated soil. They wanted to see if the plants on the site could clean the soil, and to analyze that, they needed to have these volumes of soil captive. So they decided to produce these large-scale planters, and I was helping them with the 3D printing of this process. So this was a good opportunity to test the new design of the hand of the end effector. This was also built with the help of students from the Design for Manufacturing Masters, DFM, neighbors of ours. And same principle, different execution. In this case, bullet is too heavy to just be picked by friction. So it was picked by these two plungers while it was traveling. But the compression process was performed in the same way. It was a pneumatic plunger shooting into the bullet. After a lot of testing, trial and error on the right material composition, right distance between the targets, right pressure, we finally started printing. We couldn't print on site because of logistical issues with the company that was giving us the space. So we ended up printing at the university on top of pallets. These pallets would then be loaded on a truck. The truck would go into the site, and then we would assemble the whole structure on site. Sounds reasonable, but it was a nightmare to organize and also to install. This is Satyam Gyanichandani. He's also a graduate from our master's, and we're basically doing the whole printing process, just the two of us. So I think this is also kind of proof of how much you can do with a robotic arm and the right knowledge to kind of program it and to produce the geometries in the correct manner. And yeah, these are the structures assembled at the university. This is the unloading process, which was terrible because they moved like jello. Their soil structures are not designed to be moved around, but we were forced to. Thankfully, they arrived safe and sound. We filled them with soil, and eventually they started to erode away as was programmed. We decided not to use the biopolymer on this particular mix because we wanted them to disintegrate. We wanted them to erode away in time. And yeah, they're already getting some colonization from some species of algae, I presume. And yeah, stuff is starting to grow. So we're excited to see how it ends up. So yeah, I'm gonna start reading questions in the chat because I think, oh, you guys have been answering. Yeah, no foundations because it's designed to be a temporary installation. The idea, because eventually in a couple of years they're gonna build a few buildings on that site. So it's yeah, they want it to break down. So it was designed to not last, so to say.
Design for decay.
Design for decay. Yeah, exactly. Anybody have any questions about fabrication or any of these projects? We can go to the. Okay, Chris, you raised your hand. I think you're muted. I think you're writing your question in the chat. Okay, so Walter is asking, how do the plantings react to the decay? You mean the plants that we're planting inside of the planters? Is that the question? Yes, we used local soil. Okay, so I'm gonna answer to Walter first. Yeah, so the material was okay, no, actually both questions are connected. Okay, so we started printing with soil from the site. The idea with soil 3D printing is you should be able to get to a site, take the soil from the site, use it to build with the robot. That's the best case scenario. That's the ideal scenario. We wanted to do that, but we couldn't take the robot to the site. But we still decided to use soil from the site. So we got them to bring us bulk bags, like 1 ton bags of soil that they had dug from the site. And we actually started printing with that. But then somebody at the company started getting worried about how contaminated the soil was because apparently they had tested it and they were sure that it was fine. But then somebody else said that, hey, maybe you didn't test. So at some point, somebody had doubts if they had tested the right soil or not. So they decided to recall it, which was kind of a nightmare for me because I had already calibrated the whole process and the recipe for that particular soil, and to start printing from scratch with new soil, nightmare. But thankfully, Brenda Parker, biologist and also director for our program, found this company that could give us or sell us basically a bespoke mix of soil. And we already had the data from the soil that we were using. So we were able to order with delivery and everything, and a soil that was analog to the soil that we were using on the site. So yeah, it was like, it wasn't the ideal scenario. Ideal scenario would have been that I would have been able to continue printing with the soil from the site. But given the circumstances, that was the best second option. Yeah, so short answer, yeah, we started by using local soil, but we ended up using a replacement. Yeah, the plantings. Yeah, so the idea was to get soil from the site and put it inside of the planters and plant some of the plant species that were already present there. And Brenda was taking samples from the soil periodically, so she knows how contaminated the soil was at the beginning and how contaminated the soil was at the end. So her purpose was to kind of analyze how these plants were taking up or processing some of these contaminants and seeing if there's any value in trying to promote the planting of some of these species. So eventually they were gonna take out all of the plants that were being planted there. So I guess that's how they will end up eventually. I'm not sure if they will react to the decay much, because basically the soil that we used for the structure is super similar to the soil that's in there. So I'm not sure if the decay will affect them in any considerable manner, but yeah, that's basically the purpose of those plants. Is it possible to simulate drying process as well for different conditions? It is definitely possible. I personally haven't done it, so I wouldn't be able to give you like a super technical answer, but I would presume I know there's a plugin either for Grasshopper or for Rhino called Therm that allows you to simulate the heat transfer of or even the moisture transfer of a particular bulk material. So I would presume that that could be an interesting tool to do that, but I haven't personally done it. How much organic content did the soil have? Quite a bit, actually, because it was initially it was soil brought in from the site, so it had yeah, quite a bit of basically vegetative matter that had grown in the summer, probably dried had been hydrated in the rain months and then dried up in the summer. Yeah, it had quite a bit of organic content, and sometimes that is desirable because it can reduce the weight of your unit, because the more organic content, the less dense your unit is, so the lighter it is. But too much organic content is also undesirable, because it might not help with the cohesiveness of your material. So it's about a balance of everything, you know, clay content, organic content, silt, gravel. Each one of these things has to be accounted for or calibrated if possible. What organic glue did you use to make two blocks stick together, and is it possible to use mycelium in this process? The biopolymer that I was using is called xanthan gum. So far it hasn't been used in construction much, but it is used in, for example, in some products like a toothpaste. Most toothpastes, or a lot of brands of toothpaste, have xanthan gum because it acts as a thickener. But in the oil drilling industry, when they produce these large tunnels to drill for oil, in some cases these tunnels collapse on top of these drills, and these drills are like super expensive equipment, and it can compromise the operation. So to stabilize the walls of these tunnels, they throw in water and xanthan gum, and it very quickly gels up and solidifies, so it allows them to stabilize these drilling tunnels very effectively. And that was one of the signs that I found a paper that mentioned this, and that was kind of like one of those I don't know, signs that, oh, this might be useful, you know, if it's that good at stabilizing soil and it's largely used in this huge industry, which is this oil drilling industry, that maybe there's something interesting to it. And then, you know, trying different recipes, we reached to this recipe that was, you know, quite sticky, so to say. Is it possible to use mycelium? Probably. I haven't tried that, but I know of a guy who recently graduated from a biodesign master's at UAL, and he was using root systems as reinforcement for soil structures. So he was growing this very small, I think it was like chia plants or like a very similar plant, very fast growing grass. It was a species of grass for sure. And he found that you can get the roots to grow into the soil material, and eventually the grass dies and you get the roots, you have the root system within your soil material, even if it's like more than one brick, and it binds the bricks together. That was like the first interesting thing that he found. The other interesting thing that he found is that plants above ground, they follow the sun, but roots below ground, they follow gravity. So he started rotating some of these samples after planting the grass, and the roots would start to always take the downwards direction, even if you keep rotating the element. So you can potentially have an element that has a direction of reinforcement, or he found that if he kept rotating the element every few minutes or every few hours, I don't know, he could get an entanglement of root systems in this material. So yeah, mycelium root systems, I do believe they can be used as a reinforcement. Somebody needs to test it. Like somebody needs to like spearhead this kind of stuff. Yeah, any experiments with loamy sand? I can send you a paper. I can send you a few papers actually. There's people who have done these biopolymer mix tests with all kinds of soil, silty soil, loamy soil, clay-rich soil, clay-poor soil. So yeah, there's definitely some sandy soil as well. I'm not sure about loamy sand, but hey, we can take a look. I'm sure we can find something. Cool. Sand printing. Do you mean the project by this guy who was focusing sunlight basically to melt sand into a geometry? I can't remember the name of the guy, but I remember the project. Or do you mean printing on top of sand as a support? Test a wasp printer with mixes using Santangam, and it has worked very well with the small extruders. Yeah, true. I have also used gelatin when working with clay. Works better when the clay works with proteins. Yeah, that all sounds super interesting. I will try to find some information on the plant roots guy. I know I have him on Instagram, so I can probably share his social media and you can reach out to him. He has done super interesting research. Okay, guys, so I think it's time that we get to the practical part. I'll put all the papers that I have on soil and soil reinforcement with roots. If I'm gonna check if I have any of those in the drive after the class. So yeah, so we can definitely share all of that information. And if you guys have more information, throw it in there as well. Yeah. Yeah, it's exciting stuff. Yeah, once you start looking into materials and material possibilities, it's cool stuff. Okay, so is the people who want to follow the practical part, do you guys have everything okay with the base model and the plugins? Everything's running okay? Okay, I'm gonna share. Well, let me just open the presentation. Okay, yeah, we're gonna start here. Okay. Mhm. Okay, so toolpath production in Grasshopper. So I assume that a lot of you guys must be familiar with 3D printing, at least plastic PLA 3D printing. How many of you guys, I don't know, has any of you guys printed or sent something to print? Let me check. I think, okay, Walter, I just sent you a link. So yeah, yeah, Marcus Kaiser, that was the name of the sand 3D printed. Yeah. So what usually happens when you 3D print with like a desktop 3D printer, PLA, ABS, or even resin machine, is that you give the technician a geometry of you have directly done it. You put it through a slicer. So you have a program in between that prepares your model for the hardware that you have, which in this case is a desktop 3D printer, Ultimaker, Bamboo Labs, and Ender Labs, whichever. So in the middle, you have a program that's preparing your geometry into something that this electromechanical element can transform into an actual physical element, right? These programs are usually called slicers, because the way that most PLA printers work is that it extrudes material in a linear manner according to a set of curves that have been sliced from your geometry. So you have a geometry, and it slices your geometry into a set of curves that the 3D printer can use to figure out the path that it needs to follow to produce that geometry. So that's why it's called a tool path, because you have a tool that's allocating the material, and you have a path that tool follows. Okay, cool. So I'm going to show you how to kind of the logic behind the slicer. We're going to produce our own slicer, so to say. And I'm going to, in the Grasshopper interface with the robots plugin, we're going to see how we can adapt or get the targets for a robotic arm from this toolpath. And yeah, basically, when we're talking about digital fabrication, it's super important to know your objective, like what you're trying to print, and how you can produce the most effective toolpath to print that object. Yeah, and many cases, this is what a slicer does. It gets the contouring from a particular geometry, it separates it into targets, and those targets eventually end up being allocated as material. These toolpaths usually, for more bespoke fabrication methods, require some tweaking to improve on the texture that you can get, or yeah, basically the expression that you're gonna achieve. And yeah, we're gonna see how to effectively produce one of these, or a couple of these toolpaths, one for extrusion and one for pick and place. Okay, so I'm gonna share my screen. I'm gonna check the chat to see if everybody is okay with the with the programs. Yes, so in the drive, there's a folder named digital fabrication. Okay, I'm gonna share my screen again. Let's go to the drive folder. I think it should be here. No, it's on this one. No, I don't see it here right now. Okay, I'm gonna go to the link on Miro. Okay, here on the digital fabrication folder, we have one base model. This one is just for people who are using Rhino 7. This one is for people who are using Rhino 8. And we have 3 Grasshopper scripts. The first one that we're gonna use is called Slicer, Fabrication Slicer. We're basically gonna see how we can produce a slicer of our own if we're working with, for example, with an end effector or a tool that we have designed ourselves. We are probably gonna have to set our own parameters for the toolpath. So we're gonna go like step by step on how this slicer was produced. And if you guys have any questions, if I'm going too fast or anything, feel free to interrupt me. Also, remember that this is going to be recorded and it's going to be on YouTube, so you can, check it later. Let's see what's going on. Okay, cool. So I'm gonna get started here. We're gonna produce a slicer. We're gonna get the curves for a toolpath for, let's say that you have access to a WASP 3D printer, like somebody mentioned. Maybe you wanna, one of the first things that people tend to print is like, I don't know, something like a pencil case or a base, if you have, like enough material to produce like a base. We're gonna go for the base kind of idea. So yeah, we're gonna start by, to kind of make this base a little bit interesting, we're gonna start by producing this parametric random surface. This all depends on your preference, but my file is in millimeters. If you're opening the same file that I'm using, your units are also in millimeters. For the sake of simplicity, if your Rhino file says it's in a different unit, I would suggest that you change it to millimeters. That way it's gonna be easier for everybody. Okay, so we start with a plane. We're just gonna set up an XY plane. An XY plane is basically a plane with the XY coordinates. If you give it a point to set itself, it's gonna set it at some random point, or sorry, some precise point. But in this case, if we don't set it for anything, it's gonna set itself at the origin. So we start with that. We're basically gonna build a rectangle here. So rectangle node. Okay. We're gonna use the plane as a reference. So as we said yesterday, Grasshopper inputs on the...
Some people are asking if they have, if you uploaded Grasshopper file on the drive.
Yes. I hope that you guys can see it in my screen. This is the link that is on the Miro board. And oh, you mean the plugins or the files for Grasshopper? The files are here on Digital Fabrication. These 3 Grasshopper files, the ones that say script. Let's check the chat. Yes, the drive folder that Walter just shared. Thanks, Walter. Okay, so we're gonna make a rectangle. This as I said yesterday, these nodes have the inputs on the left and the outputs on the right. Some nodes require all inputs to start working. Some nodes require maybe not all, but some of them. Okay, so in this case, it's asking for a size for this rectangle in the x-axis and a size in the y-axis. We're gonna give it 50 centimeters, so 500 millimeters. And we're gonna input that for both coordinates. Oh, I'm gonna put this to the left here. Okay, now, oh, let me turn this off so it doesn't distract us. Okay, cool. So we're here. We have a rectangle, 500 by 500. And okay, we're gonna divide this surface into a set of points. So divide surface. We take the rectangle as a reference, and by default, it's gonna give us a count in each one of these cases for 10, but that's more than what we need. Let's give it a, yeah, let's just leave it at 6 in both cases. So this is just gonna give us a reference to produce a set of vectors, and we're gonna move those points. Where's my move? Here. We're gonna move those points according to a random set of numbers. And from that, we're gonna create I don't want to say a random surface, but yeah, so to say a random surface, a random procedurally generated surface. So we get our points, and we're gonna get the vectors to move each one of these points. So I'm gonna put the point container here. We're gonna flatten these outputs. I'm gonna go later into what flattening and grafting data means. And we can put a vector container here, also flattened. This visualization. Okay, so we have a set of normals here. This is a vector. A vector is a direction, but that doesn't necessarily have a length. Now we want to move each one of these points. We can get a move node loaded here. The input that it asks from me is what geometry I want to move and what motion that geometry is going to be subjected to. So these points, we want to move them each on the X direction, but we want to move them in a random amount. So we're going to get a random number generator here. Random. Okay, we got to give it a range. So we're going to construct a domain. Domain. Here we go. Construct domain. We're gonna, so if our base has like a, we're thinking of the base, right? Let's say that it can also be 500, sorry, 500 or no, maybe 400 centimeters tall. Yeah. I can just type 400 here. Okay, cool. So that's going to be the domain end. That's going to be the tallest point of my base, of the top of my base, or like my surface. And let's go for 300 here. Okay, that's going to be the start of my domain. Okay, so we have our range. now we need to know how many random numbers do I need. So I can get here what I'm getting out of this points node is a list of points. I'm gonna talk a little bit about what a list is. So each one of these containers can either host one individual data point, and that data can be a point, it can be a geometry. These two nodes each have only one data element being transmitted. In this case, it's a surface. In this case, it's a point. It can be whatever. But as far as hierarchy in data, it's just one data element. But some of these containers have lists in them, or trees. In this case, we have a list. Lists are basically data points that have more than one element. And they have a hierarchy. The list always starts with 0. And the hierarchy in terms of order, so to say, goes from the lowest number to the highest number. We have a different kind of data that can be transmitted through these containers, and that's a tree of data. In the case of a tree, you have a set of lists, and the idea is that none of these lists have hierarchy one on top of the other. They all have the same hierarchy. In this case, we have a list that, well, sorry, a tree of lists. Most of them have only one element, but we can see that some of them have 3 elements each, and we're gonna see why in a little bit. But that's basically, you don't necessarily have to like understand it fully, but for now it's enough that we know that in some cases we're transporting just one data element. In some cases we're transporting a list of elements, and in some cases we're transporting a tree of elements. That's enough for now. So in this case we have a list of how many points? 49. Yeah, 49 points, which is unusual, but okay. Oh no, okay, that makes sense. Yeah, okay, we have 49 points, so we need 49 numbers. So I could go here and put a panel. I can type panel, and it allows me to set an input panel. I could say, okay, I have 49 points. I'm gonna need 49 numbers. I can just input 49 numbers here. You could do that, but that is not really very efficient, because let's say okay, I'm happy with my 49 random numbers, but then I decide to change this count for whatever purpose. Now I have 64 points and only 49 numbers, so this operation is not going to work. It would require me to update this number. I think it was 64, but whatever, it doesn't matter. What I can do is I can tie these two things together, so whenever I change this slider, they both work together without me needing to intervene to update that number. So I can use a list length node that gives me the length of a certain list. In this case, it's 49 numbers, which is what I need because I have 49 points, and I can input that number here. So now whenever I make a change here, the random number generator is going to be automatically updated. I can see it gives me 64 numbers now for 64 points. If I change this back to 6, we're at 49 and 49 here. So it's whenever you're working with a procedural process with a parametric modeling tool, it's usually more efficient if you can tie these parameters together as much as possible. That way, whenever you make an adjustment, everything just adjusts itself. That's kind of the logic behind it. But okay, so we have our random set of numbers. So now we are gonna set the set the motion from this plane here to something more like this. So for that, we're gonna give these vectors a certain amplitude. So I'm gonna go to vector amplitude, there we go. So it's asking me for a vector and a number. So I have my 49 vectors here, my 49 numbers. So now I have these vectors that can allow me to move these points in a particular manner. So these are random, technically random numbers between this range of 300 and 400. I can adjust the range. Any random number generator. So the randomness of these numbers is not really real. It has an equation with a particular constant that it uses to produce these random numbers. So I can input a number into this constant to change the, so to say, random result. So that's the seed. It's gonna give you different options of that randomness within the parameters that you have given it. So yeah, that's the purpose of the seed. If you have some random geometry that you are producing and you're not happy with that particular result, you can always modify the seed without needing to modify your parameters, and it's gonna give you a different result. So we're gonna build or rebuild a surface from these points. So we can get a surface from points. Surface from points, there we go. Cool, so we have our points. And it's gonna ask us for a U count, for a count of subdivisions in the U direction. And we already gave a U count for this surface, which is 6. So we can directly connect this and it should work. Now it should work, but you can see that it's not working. And that has one particular reason. When we gave a U count here, it was asking me for the count of the points in that direction, which in this case is 6. In this case, it's asking me for points starting from that initial point. So if I give it 6, it's gonna end up being 7 points, accounting for point number 0, because I'm counting from the first point forward. In this case, it's actually asking me for how many points are in that vertex itself. So in this case, I always have to add 1 to that count. Doesn't sound super intuitive, but that's how it works. So yeah, this U count, when you're trying to rebuild the surface, if you're rebuilding the surface from a surface that you subdivided yourself, you generally have to add 1 to that U count for the surface to work. Okay, so now we have our semi-random surface. We can change the seed to get different surfaces. But yeah, that's our random surface. So we're gonna, for the sake of it, this is not necessary, but for the sake of order, I like to put a container of the data type that I'm getting as a result at the end to kind of symbolize, oh, this is, I sometimes even make a tiny group and a blob with a particular color if I want it to pop in my code. But this is all personal preference, you know, like, okay, this is my surface, you know, the surface. Cool. And if I have all the viewports on, I can choose which ones I leave on or off if I think this is too messy of a look. But yeah, this is basically the process of the generation of this random surface. We have built this rectangle, and from that, now we have our surface. Okay, so to get to the point of this base a little bit more quickly, we're gonna draw freehand a curve. So in Rhino. So when we draw, we wanna keep it within the bounds of this rectangle. But yeah, so you can set to the command here curve. And yeah, just draw whatever, you know, your heart desires. Cool. Okay, so we're gonna load that curve into Grasshopper. So we're gonna put a curve container here. Curve. Cool. We're gonna, this is already selected. So, oh, no, it's not. Okay, set one curve. Okay, so this is gonna be the bottom of our base. Let me just hide these things. These points. Cool. Okay. Yeah, that's gonna be the bottom of our base. And we're gonna get a top by projecting this curve into this surface. So I can get a project node going on here. I think this is project. We want the project node that has a brep as a possible input, because there are a couple, I think. Project. Yeah, this one is onto a plane. I think that would work too. But yeah, let's stick with this one. Yeah, let's stick with this one. Cool. Okay, so we have our input as a curve. And we have our input as a brep, which is our surface. And now you guys can see that that curve has been perfectly projected into this non-planar surface. So now we can hide our surface. It has served its purpose. It's still there, but I'm just not gonna see it at the moment. So this is gonna be the bottom, and this is gonna be the top of my base. Okay, we're gonna pull it over here. Since this is where I load my base curve, sometimes I also like to highlight the inputs of my code. So I'm gonna give this a bluish color. Cool. Okay, perfect. Now we have these two elements that we can use as the bottom and the top of our base. Now, bases usually have a narrower base than the top. So I'm gonna try to do that as well. I can use a scale node. Now, this node is asking me for a geometry to scale a center, to which center it's going to use as a reference for the scaling factor, and the factor, which is by default set to 0.5. But let's say that I want my base to be just 0.75, 3/4 of the original shape. Okay, so I have my geometry. Now I just need a center. By default, it's gonna take the world center, 0.0.0. You can see that it's pulling my geometry to that side because that's not the correct center of scaling. I can get the center of this geometry with a node called area, which not only calculates the area of any geometry, but also calculates the centroid, the center point. So with that centroid, I can use as the center to my scale operation, and now it is working properly. Cool. So now I have the top of my base and the bottom of my base in the way that I want them. I'm gonna hide this one. So this is gonna need, for me, for my OCD code purposes, two curve containers. One is gonna be my bottom curve. I'm gonna hide this on the thing. This is gonna be on my bottom curve. This one, this is gonna be my top curve. So now I have the bottom and the top of my base, right? Gonna group this just because. Cool. Okay. So if yes. I know. Sadly, it helps with your scripts if you're a little bit OCD. Okay, so now we can use a very simple node called loft, which basically produces a surface between two curves, no matter if they're planar or not planar. If you want to add, there are two ways that you can merge these two data points into this one node. You can use a merge node and put data 1, data 2. We're not going to use data 3, so we can erase that one. And the result is not going to be the input for a loft operation, ideally, is a list. And the result here is not going to be a list. It's going to be a tree because it's giving equal hierarchy to both these data points. And since we want a list, we can flatten this from a tree into a list. And now that we have a list going on, we can use our loft node. And okay, this is a very common error when working with loft and curves. What's happening here is that it's recognizing both curves, but one curve is going in one direction and the other curve is going the opposite direction. In Grasshopper, in Rhino, curves have a direction, and that has a very simple fix. The only thing that we need to do is just to flip one of these two curves. So we're going to use a flip node, flip curve. We're going to flip this one because why not? And this should be fixed. Okay, now our loft operation is working properly. I think this is too open, too flat of a base for my liking. So I'm going to change the factor to 0.6. Let's see how it looks now. Okay, that's a little bit more base-like. You know what? 0.5 is the thing, I guess. Cool. Okay, base. Perfect. Okay, so in terms of 3D modeling, if I wanted to print this with a Bamboo Labs, with an Ultimaker, with a 3D printer, this is where I would stop. I already modeled my base. I'm gonna put it into Cura, the slicer. The slicer is gonna produce the G-code, and the printer is gonna print. Full stop. That's where the creative process would stop. But what we're trying to do here is to produce our own slicer, right? Our own way, our own bespoke way to slice and to 3D print this model according to an equipment that we might have, or maybe we produce a different material. We have produced a biomaterial that can be extruded. And that material has particular properties. So the slicer that I use for a desktop 3D printer is not going to be good for me. So I need to learn how to produce my own slicer according to my own parameters. And that's what we're going to try to do now, or at least the concepts around it. Okay, so the first slicing operation that we're going to perform, I'm just going to use the same input here so we can preview it here, or maybe here. Yeah, that's it. Okay, yeah, the first slicing operation that this needed to be flipped. No. Okay, never mind. Yeah, we're gonna do a regular slicing operation called contouring, which gives you I'm going to show you with the geometry that I prepared for the class. I'm just going to disconnect this so I can show you. Yeah, we're going to do a planar contouring, which is, so this was my geometry, the geometry that I produced when I was testing this for the class. We're going to do a planar contouring, which is when you, basically what 3D printers do, which is just flat contouring toolpath. If you see it from the side, it's completely flat. And we're gonna produce an adaptive non-planar toolpath in which the path of the printing follows the shape of the geometry. So you can see that from the side, it's kind of not flat, so to say. Although I think we're running out of time. So we have two options here. Since I already showed you how to produce the geometry, I can give you guys, well, you guys already have this file, both the non-planar and planar are coded here, and also how to get those to be, to have, you know, thickness and movement. So you guys can explore the tool and we can go straight to how to adapt this to the robotic arm. Or if you guys prefer, I can continue with this part on how to tweak and play with your toolpath. What do you guys prefer? I'm gonna leave this up to both. To voting, sorry. The toolpath. Okay. Okay, so yeah, I think that might be yeah, it's interesting to see how you, because when you get to produce your own toolpath, the way you break free from the constraints of, oh, it has to be a straight line and it doesn't have any kind of expression. You have a little bit more tools. So I think it would be interesting to explore that part. But to keep it quick, I'm gonna go step by step on the geometry that I have produced, just to make it a little bit quicker. Okay, so I'm just gonna go through the script that I had already done. So you guys can already get to this point where you can, you know, model something to use as an excuse to produce a toolpath. But okay, so we have our bottom curve, top curve. We have produced the loft operation to get the geometry. And now we need to contour it, to produce these contours, right? So this contour node requires a point as a reference, which is the same point that we got from the beginning from our centroid. So we can recycle that one. A direction, in this case, we want it to be straight up in the set direction. So that's by default set up. But if you want to be like super OCD, you can put a unit C node here. Okay, unit C. Same result, because that's the default setting. By default, it's gonna do your contours from bottom to top. And this is the first point when you get to calibrate something for your toolpath process. You can set the distance between the point. This distance is gonna be the distance between your layers. So here I'm imagining as if I were printing with a WASP printer with clay, and I said, okay, let's give it a 5 centimeter layer height. 5 millimeter, sorry, it's 5 centimeters would be huge. 5 millimeter layer height. So I'm inputting 5 here as the distance for my contours. And yeah, that gives me my planar toolpath. And that could, you know, be enough. And you could get, I'm gonna copy this. This is my little visualization tool. You could get already a 3D print from this. Oh, sorry, my bad. Yeah. So what we have here is basically a pipe node, which is gonna give thickness to this lines from the toolpath. So we can kind of visualize how it would look like if I 3D printed it with a WASP 3D printer in clay or something like that. So we're gonna go to the Arctic view. This might take a second. Oh, that's already there. Okay, so just gonna turn this off. Oh, should turn all of this off too. this one, by, and by. Okay, cool. So this is how it would kind of look like if we printed it with clay and we just conformed with this planar toolpath iteration, which is okay. I mean, it would still look cool. I think my mom would love it, but it's not really that exciting, and we can do better. You know, Grasshopper allows us to do better. So what if? So these are basically a set of targets for the robot. What the robot does is it takes each one of these lines and it splits them into a bunch of targets, numbered targets, and it goes from one target to the next. So we can manipulate those targets to maybe get a texture going on here. So yeah. So in this case, we're working with, okay, well, let's go super quick to the non-planar one to see how that one would look. Yeah, so we have also a non-planar toolpath, right? We can also visualize how that would look like if it were 3D printed. Are we in Arctic? Yeah, we're in Arctic. Okay, cool. Yeah, that one looks a little bit more interesting, less flat, doesn't have those like sharp ends where the extrusion just stops. And this is already like a step forward from what you can get from a regular 3D printer and a desktop 3D printer, but we can do even better than that. So let's take a look at this. So in this case, to get those non-planar curves, we have used a twin node. A twin node, what it does, it gives you the average between two curves. So for example, if I were to produce a new twin node, I can take curve A, curve B, and by default, it's gonna give me the middle average. Like these are my two extreme curves, and the one in the middle is the average. The average in every aspect, like in position, in shape, in scale. But if I give this twin node more, right now the factor by default is 0.5, so the dead middle. But if I give it more factors, it's gonna give me more of those curves according to the number that I give it. And this number should always be between 0 and 1, because 0 is gonna be the first curve and 1 is gonna be the last curve. So I can feed, I could do a panel and be like, okay, what if, quick tip, if you're putting more than one data point into a panel, you want to put multi-line data because otherwise it's not going to read it. So I could say, okay, let's do 0.25, 0.5, and 0.75. So that's going to give me 3 curves. Cool. Yeah, that works, but it's tedious, and it also doesn't give me the possibility of figuring out how many contours I need for my extrusion distance, which we have decided is 5 millimeters, right? So I need to figure out how many factors I have to feed to this twin node to get enough curves so I can have my 5 millimeter layer height. So what you do in that case is we need a list of numbers, namely this list of numbers. But how did I get to this list of numbers? I had to basically find the height of this element, to divide the height between those 5 millimeters to figure out how many curves, how many subdivisions I need to get to that layer height. So again, I'm not gonna reveal this because it might take too long, but I'm gonna go node by node. So we took the geometry, we built a bounding box, which is a box that fits around your geometry. This is a deconstruct box node that basically analyzes your box and gives you its properties. In this case, it's telling me that in the Z axis, it goes from 0 to 307 millimeters. This node gives me the highest number in that list, which is the height, which is what I need. The height was divided between 5, which is my layer height, with this node, which is literally called division. Division. There we go. Yeah, you have a lot of mathematical operations here at your disposal. And we get a result that's not really a number. We need a number of layers. We need a full number. So this node rounds that result. So those are my steps. My domain goes from 0 to 1 to get numbers from 0 to 1. And my steps are 61 steps because that's what the program is telling me. That's the number of layers that I need, 61. So it's giving me 61 numbers equally distributed between 0 and 1, which is precisely what I need. And that way, my twin node gives me all of the numbers, all of the layers that I need for a non-planar 3D printing method. I've gone through it super fast, but this is logically quite simple if you analyze step by step what's happening in the algorithm, which is for that I find useful to use this little button here. These are simple operations that allow you to have much more control than what you would get from a off-the-counter slicer and a regular 3D printing process. So, okay, this is already kind of cool, but we can go a little bit further than that. We can take these curves, split them into subdivisions, and move these points a little bit out or a little bit in to get a wavy pattern. I'm not going to explain that part because it might take too long, but we can get a wavy pattern on the toolpath. So our final result, sorry, can have a wavy pattern on top of the geometry. So we can try to visualize that if my computer doesn't crash, because this pipe operation can sometimes be quite heavy. Okay, that's not too bad. I'm gonna turn this off. Okay, that's off. Yeah, we should be able to see it. This doesn't collapse. Yeah, I don't think I should try to host one of these meetings and run the scripts. But here we are. So the idea is that when you have control not only on the thing that you're designing and the way that you want roughly the element to look, but when you have control on how it can be built or extruded or, brought into a real world, the more control you have on each one of these processes, the more control you can have on the result. And yeah, I do believe that having in mind how your geometry or your base or whatever project you're working with, when you have knowledge and control on how it's going to be built, it affects dramatically the design, the final look of the thing. I think it's a much more informed process. And I don't think this is gonna, yeah, this is gonna crash. I think overextend. Yeah, I overexerted this PC. But yeah, that's roughly the logic behind that toolpath production. The file is there, so you guys can check it calmly step by step. And if at any point you have any question, just shoot me a message, shoot me an email, and I can help
It's a
you.
workshop. Yeah.
Sorry? Oh, I think somebody turned on their mic.
Oh my God, sorry.
Yeah, no worries. So I think we can get a break here, maybe 10 minutes. I can then show how these toolpaths are adapted to an extrusion and a pick and place script with the Grasshopper plugin. So you guys can, if you want to take a piece of your project and animate it as if you were extruding it or building it brick by brick, we're going to show that. It should be quite simple. And then we're going to let you guys work on your project. We don't expect everybody to introduce, the fabrication simulations into their design if they don't feel it's super important. But if any group feels it could be important for the process or it could inform their process, you're more than welcome to introduce it as well, and we're here to help. So we'll be back in 10 minutes at like 5 past 12. Is that okay? Okay, cool. I'm gonna stop sharing. Pause. I have to stop there. Yeah. My bad, part 2. Okay, cool. So we built this tiny wooden platform to have the robot always pick up the bullet from that position. So yeah, we were producing the bullets in bulk, but we were placing them one by one on top of that tiny platform, so the robot could pick them up one by one. Yeah, we weren't trying to get the robot to pick it from a pile of rubble or anything like that. Yes, you have that Grasshopper file. It's in the drive. It's called fabrication extrusion script. Let's check your error. Okay, yeah, okay, that's can you go to the panel of the output of the error so we can check what the problem is? Here, Thomas. Oh, target out of reach. Okay, that means that for some reason, let's see. The reach of the robot is limited. It has a range of, I think it's 1.8 meters from its base. So if your geometry is too large, like for example, let's say that, okay, let's bake this into Rhino. And I'm gonna scale this up dramatically, okay, like that. And I'm gonna make another container and I'm gonna load this set multiple curves. Okay, cool. Okay, so this container now has a huge version of this thing. I'm gonna erase this. Oh, sorry, internalize. Okay, now I can erase this. Oh, sorry, again, not sharing my screen. I'm gonna share my screen again. Cool, okay. So we saw that the script was working with this geometry right here, which is regular size, so to say. Let's give it a try with this other geometry, which is much larger. So I'm gonna connect this here. It's gonna take a second to basically tell me that it can't do that because it's too big and it's probably some targets are out of reach for the robot. So yeah, I'm getting an error. And it's telling me overhead singularity. So in this case, the model is too high and it's not getting there. Like it's trying, it tried to start and it gave up at that point. Like it's not happening. So when you get an error, first of all, it's useful to check what kind of error you're getting. In this case, it's an overhead singularity, it's too high. And you have a few options. You can see if you can adapt your geometry so it doesn't go outside of the reaches of the robot, or you can, for example, let's say if your robot was at the same height as the table where you're printing, and your print ends up being too high, and the simulation tells you, oh, overhead singularity, it's too high, we're not gonna get there. You can try to move your printing plane down if height is the problem. If maybe your model is too far away from the robot and the robot is not reaching and it tells you, oh, target out of reach, you can try to move your printing plane closer to a robot and you input that into the calibration because the robot in the end is trying to print on the, no, this is the tool setup, this is the work frame setup, on the space that you have basically told it to print. In this case, this is the workspace setup. So it's within the range of the robot. So if I move this, if my geometry is too big, I can move this workspace through the calibration closer to the robot so it doesn't overreach. So it doesn't have problems reaching all of the print. So these are all things that you have to know your hardware, not only the limitations in terms of sensors, but also in terms of what is the reach of my equipment, both in the XY plane and in the Z plane. How high can it get? Is my geometry too big? Is my geometry too far away from the robot? So these are all things that you have to take into consideration. Maybe if your geometry is too big, maybe you don't print it in one go. You set the robot on one place, you calibrate it, you print a section of your geometry, and then you move the robot. Or maybe you use two robots, or maybe you use a bigger robot. So all of these are things that when you are attacking your project, you have to figure out, right? We recently did a competition with a friend where we were trying to introduce this fabrication method, and we had to figure out the design according to the reach of the robot and how many times we could allow ourselves to move it around with the time that we had. So we decided on 6 positions for the robot, and most of the construction had to happen around those 6 positions. So that's kind of the mindset that you have to get into. Okay, anybody else have any question on this extrusion script? If not, we can quickly move on to the next one, which is very similar to this one, but a little bit more complex, which is the pick and place script, which is the script that I developed for my project, which is super similar to the ETH soil clay fabrication project. So similar scripts. If everyone's cool with it, I'm gonna open the next one. So again, you can go to open here. It's the same base file, and you can go to the pick and place script. Yeah, no, ignore the file. So it has the same bones as this one, but it is a little bit more complex for a particular reason. In this case, as you guys saw in the video, in the case of the extrusion script, you tell the robot to go to the first target, and then it just goes to target 2, 3, 4. It just continues as the tip starts extruding material, right? So it's a continuous path. In the case of pick and place, which you could relate it to like bricklaying, when you're building a wall with bricks, you need to entwine those targets for the geometry with the pickup target, because the robot, it's not going to do this continuously. It's going to come and go. I can show you guys the logic behind that in the simulation. So basically, here, this is the input for the geometry, this turquoise node. And you guys can use this sample geometry that I left in the file, load it here as set1 geometry. Just gonna think about it for a second. Yeah, there's somebody, time is running out. Okay, cool. Yeah, same logic. Sorry, same logic as the other one. You have your tool calibration, you have your workplace calibration, but you have one extra calibration, which is the pick plane, where you're going to pick up the material. So you place the material on your workspace, you pick up the material on your pick plane, and you have to entwine those targets. So that's where this little weave node comes into the question. It's telling the program which target to go to first, second, third, etc. These are the commands for the compression. And if we see the simulation, yeah, it goes from bottom to top, but going iteratively into the pickup plane. I can turn on these lines so we can see it more clearly. Yeah. It's going from the pickup plane to each one of those planes, putting the bullets as if they were bricks. And yeah, I'm going to turn this off because it's too, yeah. And here as an example, I have put, you guys can explore the script when you prefer. This is a non-planar toolpath with the pick and place script. And this is the same geometry with a planar toolpath. So both valid options, different properties and different look. So yeah, this script is also there for you guys to look around, explore, play around, input your own geometries. This script is designed for larger scale things. You can change the size of the brick of the bullet here. You can change it on this side of the thing. Yeah, just try around different geometries, see what works for you. It's there for you guys to use. And we're gonna go to the working part because we don't wanna lose too much time. How can we simulate the releasing of the bullets in the code, or is it only in G code? So here we're not really simulating the release system. We just want to run a simulation that can allow us to see if the robot is gonna be able to handle that toolpath or not, if we're getting errors, if we're getting any kind of concerning things in terms of safety. So this is not really simulating the bullet release. If you check the script, it's merely all of these bullets that are appearing. Technically, they're already there. The only thing that's happening is that I set up this split list node, which takes a list and it splits it, sorry, at a particular number between this is seen and this is unseen. And the index for that number depends on the running, it's this index here. So the more the program runs, the more of the structure we're being shown. So this is not really a simulation of assembly. It's merely a script to visualize the assembly process. But if you wanted to, you could animate the process of, you know, opening a claw for bricklaying, or even this plunger process. You could animate that. It wasn't really the purpose of the script. If you guys wanted to get an animation of this for a project of yours, for example, you just set up a viewport, and this animation control, you can put a slider that goes from 0 to 100. Actually, I would probably give it a little bit more subdivisions because otherwise it's going to be super choppy. But yeah, 0 to 100 is just as an example. You connect it to the time of the simulation and you do right click, animate. And this is going to allow you to animate that slider, and it's going to, no, this is, we need to get a little bit further out so it will be able to see something. Yeah, so you want to give it a decent amount of frame counts. So usually you want around 20 frames per second. So if you want a 5-second video, it's going to be 100 frames. So we can put 100 frames here. You choose where you want to save it. I don't care for now, so we can leave it at that. And you press OK, and it's going to start animating step by step the process. And it's going to give you the frames. The frames, you can then process them in Photoshop or Adobe Premiere, whatever you prefer as a software. And you can get an animation on the fabrication process as well. I'm going to stop this. Yeah.
Great.
Yeah, so yeah, the script is there in the Drive folder. You guys download it, explore it. If you're interested in it, send me an email. I can help you later. But right now, I think we should, as Dana said, we should go to the work part of the thing.
Yes, unfortunately, I know that a lot of you need to go in an hour. So yeah, if you can work on your project for, let's say, next 40-50 minutes, what do you guys think can add?
I think that sounds good.
Yeah, and we leave the last 30 minutes for presentations. We can just go through Miro. You don't need to create a presentation. We'll just go through Miro. And yeah, thank you so much, Kenneth, for showing your incredible project. A huge fan of soil fabrication, the research there you are doing. Okay, great. We will stay in the main chat. Should we join? Yeah.
Yeah, rooms are open.
Rooms are open. Great. Yeah.
I'm gonna start closing the breakout rooms. They should close in like 60 seconds. I think if some people, you know, want to polish more these things and maybe have like an informal call next week or something, I would be totally down to see what they work on. Like if you guys feel like you'd be okay with seeing it, maybe we can mention it.
I mentioned it.
Maybe nobody will want to, so that's always a possibility too.
Ended up mentioning it in group 6 and they were like, yeah, they would love that.
Okay, that sounds cool. And
yeah,
we'll mention it at least.
They're down for it.
See who bites. Okay, I think we're all here, right?
Mm-hmm.
I think the breakout rooms are closed. Okay, cool. So does anybody want to take the lead on showing what you guys have on the Miro board? If you feel like you still want to polish things and maybe check them out in a few days, we were just discussing with that, we would totally be okay with maybe setting up a meeting next week whenever it's just an informal meeting, just as a discussion to discuss the projects and everything. If anybody wants to organize that, we'd be happy to just give you guys some time to work a little bit more on these things. We know it's been a super short time, so we're going to consider that if we ever decide to do this workshop again. But yeah, if anybody wants to meet next week, we can talk about it. Apart from that, if anybody wants to take the lead to show us their work on the Miro board, this is the time.
Also, it would be great if you could turn on your video so we know how you look like while
That
you're
would be
presenting.
great, yeah.
Yeah, that would be great. And so again, you don't need a final product. We just want to see your progress and discuss with you, and just discuss maybe further developments if you'd like to take this project further in the future.
Guys, I just want to take this few minutes that we have while you guys get set up to really emphasize the fact or the idea that all of these projects, since they are very complex, are usually very collaborative. There's a lot of people involved. All of the initial material explorations that I did them with Dana and with Leticia. We all worked together on the first year. Then all the work that I did for the thesis was done also with Leticia and Itamar Lilienthal. It was a collaborative effort. That project that I showed you guys on the video, that was done with Marcos Cruz, Brenda Parker, the program directors, robotic technicians, Guillem Peruxet, Yao Meng, Yifan. Yifan helped a lot with the printing process, Yifan Shi,
Satyam
Yanichandani, Achu Ayelen Franceschini, Argentinian architect. She helped with the modeling and their initial renders. So yeah, it takes a lot of people, and it's always important to not only credit them, but also to spread awareness that these are collaborative efforts.
Absolutely.
Who knows, maybe at some point, some of you guys might have an interesting project in mind, and we might be able to help you. So it's important to drive down the idea that this is a community behind this whole effort.
Mm-hmm. Yeah. So we dislike the one-person architect idea, essentially. It's always a collaborative effort.
Right? Yeah. Like the studio projects that, hundreds, well, sometimes at least sometimes dozens of architects are involved in, and just this one guy who gets invited, right?
Yeah. So Nadia, would you like to take a lead?
Yeah, sorry, I forgot how to
Share?
raise hand, so I was trying to figure that out.
Yeah.
Okay, so let me just go share screen on what we've done. I know you guys.
That's great. I think if each group can have 5 to 7 minutes, we can wrap up, in 20 to 30 minutes.
I'm just gonna put us on our ones. I can go through a bit of the concept, and then I'll talk a bit about the concept, and then my teammates will discuss a little bit more on the physical structure. So yeah, basically we had a site in Blackpool, as previously discussed, that had a big problem with pollution. We kind of wired it down to this, like, kind of the major factors we wanted to focus on. So we looked into native plants that could purify the water and seeing what actually the water, what big bacteria or pollutants there were. And one of the big ones is E. coli. And we found that something interesting to pick upon, as algae and E. coli have an interesting relationship, as they can either feed each other or compete with each other. So we kind of wanted to make sure that algae was, we made this structure that was a biosculpture inspired by natural organisms, and it'd be a smart microhabitat. So these are kind of the starting, just conceptual things we did after our research. So we have the design experimentation. So, sorry. So Evelyn kind of came up with this structure that would go along the beach side. So staying near the water. Basically, we kind of turned it more into, we have this structure that would be submerged in the water. So it can actually function. It's not just like a physical thing. It would also be able to function, and it wouldn't just be the sculpture is separate to the actual device, that it's one and the same. So it actually holds the macroalgae at the bottom of the sculpture. And we thought to add a dock, because then if we add a dock, then it's a bit more interactive. And people nowadays, they love, like, whenever you see a dock with like flowers or anything like that, people love to take selfies, all of that. And I love, whenever we go on the beach, there's a dock, I like to sit on it and draw. So we kind of did that as a team, had that idea, and it's a rough sketch, but just showing, when I was doing the research, the macroalgae attracts the microalgae, if I'm correct, or away from the top water. So it essentially, it oxygenates the water, and it allows for less of that, basically of the E. coli feeding the algae, from what I read, because we read some papers and we were doing some big research on that. Yeah, and then we have these tiles that Evelyn and myself, and we worked on further with my CPD, working more on the sculpture. But yeah, and I'll show you more of the biosculpture here. So we came to this form, and I don't know if CPD, you want to come on the call, if you want to explain this a little, or I can explain it.
That would be great
Yeah,
if you explain it. Yes,
I
thank
can
you.
explain it. Yeah, no problem. Okay, so basically we went forward with this biosculpture, which would go in the water. So it is similar to the dock idea. It's just we didn't have enough time to mock it up fully, but that's more, it's more to show what this little structure and all the sketches have been. So it would be curved, as this would be deeping into the water. So it would be that part that dips into the water, and we would have the bridge upon this side. And it was really like various cells that are able to host different types of species, which would be able to coexist together and create a mini habitat over there, which would draw it away from, because a lot of it's just all on the surface, and it's not making, people don't want to come to the beach as much, because there's all this like scum and just a lot of debris in the front, on the top surface of the water. So kind of attracting that away and having it in a more singular area, we think would be better. And through, for example, the tiles that Evelyn worked on, we saw how the water would actually go through, and you see all the microalgae, how it build up in between all these little grooves. And yeah, and there would also be holes through to let water pass through, and any like small fish or anything like that. And yeah, so that's kind of our rough kind of idea, or like solution to the area, just trying to solve at least a small part of the problem. So yeah.
That's super cool. I think yeah, you came up with kind of these two different proposals, and both revolve around the same ideas. I think both are quite interesting. I think you mentioned something about algae and the E. coli bacteria.
Yeah, so basically when I was doing research about it, it was saying that basically when the algae goes through the photosynthesis, their own photosynthesis process, it basically feeds the E. coli. So trying to take away that microalgae away from the top surface of the water and letting it also be the feed for the macroalgae was to basically try and steer that away from the, what is it called, the water pole, if I'm correct. And as it usually breeds around there. And when it's in my algae, E. coli also it thrives in sunniness. So if we bring away the microalgae away from the very sunny parts of the area and have it more the shade, I feel like it would kill it off more. So it has less chance to breed as much because it's the only way to turn it into competitor between the E. coli and the microalgae is to essentially either the pH is raised or factors change, like the amount of sun. So yeah, that's kind of roughly.
That sounds super cool. Yeah, and yeah, this is actually what you're saying is super cool, but also this whole situation is super cool because yeah, this has been a very fast exercise, so we couldn't expect to get like a fully polished product out of this. But just this conversation and what you're showing me and the research that you've done and how you're tying the research and the study of this organism to the intentions of your project, this is exactly the kind of conversations that would happen in the realm of the masters that we just did. So this is exactly what we wanted, the process that we wanted you guys to go through. So yeah, this is super cool. I like the project. If I, for example, wanted to think about for the next steps, that biosculpture looks definitely fabricable, but I would presume that maybe not exactly like that. In my instincts tell me that it might need to be a little bit more dense it can be, very much like that, like this Voronoi almost pattern, but I think it would need to be a little bit denser. But that would mean that you could have like different sizes of holes that might have like different bioreceptive properties for different species. I think it's you have like a few exciting avenues to explore. So yeah, I think it's super cool. Like I think it's going super well.
Thank you.
What do you guys think?
Sorry, I have a question about the density you mentioned for a sculpture. By density, you mean that the cells should have smaller size and be
Probably.
so the bigger size cells wouldn't actually function as we want to.
I think they could, but maybe you could have the bigger size cells more on the top part, because structurally, for the bottom part, which is going to be the most load bearing,
Yes.
I think that part should be a little bit denser, and maybe on the top part you could have like the bigger holes, much lighter. But I guess then the next question would be, okay, so how much of the structure do we want to be like underwater, or in this space where water goes up and down in the high tide or the low tide? So that would probably mean checking what's the difference between high tide and low tide in this location, then choosing. So each new question comes with its own new set of questions, right? So
Yes.
yeah, but those are just ideas that you guys can take into consideration. In some cases, it's also important to know when not to listen to what your tutors tell you or the people that are talking about your project. It's don't take everything that I said for granted. Do your own explorations, and definitely follow your instincts, because I think they're leading you in a good direction. So yeah, super good, guys.
Thank you.
Thank you.
Yeah, great project. Really fantastic idea. I will be very short because we have to move on to the next group soon. I would agree with Kenneth with the porosity sizes. Perhaps the microtexture sizes could be different. You know, the material gradiency, for instance, if you are creating from crushed seashells, a biocement, let's say, or with calcium carbonate, perhaps you can experiment with different pH and or different porosity, and parts can have different porosity for this, you know, this type of organism, and the other part can have like denser porosity and perhaps like smaller porosity for other organisms. So, you know, you can play around with the gradiency. I think it's a very promising project if you develop it further, and visually it looks very interesting. You can definitely combine perhaps height fields microtextures with Rhino branching, like cell system. Yeah, overall, very excited. Thank you, guys.
Thank you.
Yeah, just real quick, interesting piece and good work. I think all of the comments they made is under the context of materiality. So that's just something to notice in the process, is that when you get to this point and you have to consider a material, that's when the design and fabrication process kind of start playing back and forth. And so you're at a point now, which is great that you reached the point within 2 days to where now you can consider materials and then develop a design around that context.
Thank you.
Shall we move to the next group?
Yeah, let's do
Yes.
I'm just seeing that a lot of people are leaving, so
it.
we should hurry up. Yeah.
Maybe room 6. I know we were talking to them earlier.
Hi, I'll present the group. It's room 7.
Cool.
Cool.
Okay, let me share my screen. So the site that we have chosen, or we can say we have been introduced by Walter, is the Burner Gateway, which is in New Jersey. And before going ahead with everything else, so I want you to understand why this is important, or why we agreed to go forward with this. Is that this area has been quite heavily eroded due to the climate impact, or you can say the rising sea levels and other flooding and hurricane events that have been happening over here. So it is quite interesting to see how, and to know the perspective of somebody who lives there, that how this area has been affected and had been turned out due to this climate impact from past few years. So that is why we agreed to go forward with this site, which is located in New Jersey. This problem has already been identified, and few solution has been proposed by lots of people over there. So as you can see, there are few problems with the site, that you can see the scalping and the broken off of the erosion, as well as few others exposed root systems over there. So here are few solutions that have already been tried to implemented at that location, like this geotubes you can see, which has been installed in 2010, and you can see how it has grown, and how it has helped somehow there, and its situation in 2016 around. Few of the MIT researchers have also been tried to fill up with the seashell bags, and this is how few of the solutions that has been implemented to resolve the problem and to redefine the seesaw. So while learning about this site, we have tried to identify few of the organisms and the indigenous species over there, like this oyster castles that has been installed by an engineering firm. They have been tried to install this oyster castles around the area, and how it has grown, the oysters have been grown over that place. So our main idea to understand the problem and to figure out a solution took us to understand what type of coastline it is. Obviously, we'll do a few more research to better understand the issues, but we have been trying to understand what type of coastline, what is the erosion rate, and what is the pattern of wave and the environmental regulation over there, which will help us to understand and identify a better solution, as well as to give us explore more, help us to explore more ideas. So Bala, maybe you can carry forward and explain the solution and the conceptual development that we have tried to come up with.
Yeah, thanks a lot, Monica. So going through the solutions that were implemented, I think I can share my screen. Maybe. Yeah, thanks. Thank you.
Bala, you're also a little bit muffled. And maybe if you can clear the mic a little.
Really? I'm not audible right now?
It's hard to hear you.
Oh, sorry about that. I think it's happening a bit frequently. I don't know why.
Okay, it got
Am I
better
audible right
now.
now?
You're
It's
better,
better
so you
now?
can go for it. Yeah. Maybe just
All
speak
right,
up
all
and it'll
right.
help.
Yeah, all right, thank you.
Mhm.
So yeah, the solutions that were already implemented on the site, uh, that is that had happened not exactly on the site which we selected, but in and around the site. So it comes in the same biodiversity. So through the morphological evolution of the solutions that were implemented, we could able to see that how the microorganisms and the diversity has been developed by the support of these installations. So we could see that how the evolution has happened right from the geotube, and it goes till how they are trying to figure out how the 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 installation, I mean, the structures were made sustainable at the same time, giving its ideal ideal result. So also we could see that how oyster growth has been accelerated due to this, due to the geometry, and particularly right at this place. And there are plenty of studies that are showing that oyster organisms having a growth pattern due to this um, uh, implemented structures over here. And so through this, we came up with an idea where it is very primitive, and sorry about that we haven't able to develop this uh, further. So the idea is to initially we thought we could use the mangrove roots, which had this fibrous geometries within it that has both um, that has both voids and gaps within it. So what happens when over the time this oyster has its own growth pattern, which could accumulate between these voids and gaps and form a natural barrier for the coastal system. So likewise, we were surfing around all the ideations and natural systems that could enhance the native biodiversity. So we found this in terms of geometries. So we found this mangrove roots have this very fibrous geometry, and few of the reef systems which are found near coastal zones are pretty much solid. So we kind of try to implement both these solutions by getting inference from the previous solutions that were implemented. So the inference were over the time the reaction would change, and it does have an evolution. So we try to elongate the particular reaction when these bio structures were installed. So we thought we could install two typologies, two prototypes. Basically, prototype one would be the mangrove branch, the mangrove roots with voids and gaps. So the geometry one with voids and gaps would be designed to be decayed, like as Ken once he was explaining his project. We kind of slightly aligned towards the ideation. So it is, yes, it is designed to decay. So one prototype was designed to decay and one prototype was designed to be settled right at that place. So the prototype would be, so the second prototype was designed to decay. So this prototype could be made using biomaterials which can erode bacteria that lets the indigenous plants and moss to grow very well. And the first prototype, the mangrove one, would be the another clay composite material which could be 3D printed using any machines, 3D printable machines. That would be encased with the second prototype, where after a certain time, the second prototype that is going to be this soluble, eroding element that has this bacteria that lets the plant grow and enhance the native indigenous species and enhance the biodiversity. So the second prototype dissolves and helps the system to accumulate the oysters within the first system. So hence the first prototype, which is the mangrove geometry, could interlock by itself after the erosion of second prototype. So we have made some prototypes for eroding geometries and as well as for this skeletal fibrous system, which could more replicate like the mangrove fibers. And so some of it were so we haven't decided the ratio of both these prototypes, that how it is really gonna work, and the actual geometries and ideal geometries, and we haven't really worked on optimizing the geometry yet. It is very primitive. The idea is very primitive, and we came up with very organic forms, very primitive forms. Even these are from minimal so we took minimal surfaces. The reason is to make the to make the soluble one, I mean the eroding prototype, very minimal, so that it doesn't harms or affects the system in an opposite way. So we were very skeptical about it, and we had introduced all those minimal surfaces could help in some way to to support this sort of mangrove fibrous system. So that's how we blend both the prototypes and came up with some ideation, and still we are working on it. And yeah, if anyone wants to add up some more point, please.
Great. I think you guys did a good job of kind of like finding a problem and the solution and kind of collaborating on concepts. It seems like you guys have like a realistic approach on the process, and kind of it's really cool that you guys are going for something that's a mix of like a degrading and an object that stays in place on site. I think it's something that comes up in conversation is like, do you want mix of two or one? It's well done. I think the first thing I think about when I look at this mix with this units is there's these methods that people attempted in the program over the years in the past that have had printing in layers and then placing like a because the reason why they would do this, so what I'm trying to explain is like complex forms are difficult to print, especially branching structures. So often what people try to do is make it in layers. So they'll print a part and then they'll pack it with a material in the surrounding like platform, and they'll keep printing in layers and surrounding it. So a good example is Kenneth actually for his pick and place structures, for it to dry properly and solidify, he would have
I
stacked
think
bins with packed soil that layered up. So that's one fabrication method that I feel like would work for this if you wanted to try it.
exactly like how this SLA printing system works, right? SLS, yeah.
So that's, yeah. So except the differences is that the differences here is that you get to use a biomaterial that just stays instead of pulling out the powder. So
Yeah.
you would then just be able to bring it, which is like kind of skipping a step in a good way in the process and bringing it directly
Yeah.
onto the site just as the brick. It's quite cool.
Yeah, that's right.
Yeah, I think I agree with everything that Edward said. I think it's also super cool that I understand that you guys are still polishing your design, but you're starting to tie the concepts of these natural processes with these computational tools, like you talked about erosion and how you were considering on using minimal surface geometries to be mindful of the interaction. So yeah, that's exactly the connections that you should be doing, which is super cool. I think the only thing that I would comment is maybe it's a good moment to start focus. You mentioned a few specific organisms like a set of bacteria. Maybe doing a little bit of deeper research on what this organism is or what bacteria it is exactly, because the one that I mentioned, for example, in our project, it's a bacteria that is in soil, and what it does, it breaks down the nutrients in the soil for the plants to uptake. That's why it enhances plant growth, because it helps the plants process these nutrients in the soil. But that exactly the same bacteria that wouldn't work in a waterfront environment, because it wouldn't stay in the soil, it would just get washed away. So sometimes it's useful to take a good look at these agents that we're using to choose the right one. But other than that, yeah, super cool. Super cool exposition of ideas and processes. I think you guys are on the right track, and yeah, thanks for sharing your work.
Sure.
It's
Yeah, sure. We'll do that. Yeah, sure. Thanks a lot.
Great project proposal again. We'll have to move to the remaining 4 groups because it's running a bit late. Thank you, guys. Okay, next group. Perhaps Karagöz. It would be great if you guys can turn on your videos as well.
Hi. So I was working alone. Unfortunately, my group decided to not to work from yesterday, and I've been just trying out some patterns with Houdini high fields. And if you want to see it, I can show it. Otherwise, I didn't go that deep to solve a problem. Yeah, I had my own.
Yes. No worries.
So can you see it?
Yes.
Yeah, so as I was thinking that we'll continue working with Nami beetle from the desert and its shell structure. As I already said, it contains of these bumps and cavities. As you can see here, it's like the macroscopic zoom in of the shell structure. And the bumps are considered to be hydrophilic, so they absorb and catch the water droplets, and the cavities should be hydrophobic. And I sought to recreate this pattern utilizing high-flow tools. Yeah, so I just did as Dana told us to do, and it worked out. I will experimenting with some parameters to get some like more irregular patterns to see bigger, smaller bumps and cavities to have more diversity in the pattern. Yeah, then I did the volume, and I also applied the noise, but then I did the erosion test to see. I did run the precipitation erosion simulation to see where the water would collect. But yeah, I'm not that much satisfied with noise parameters I ended up applying on top of the pattern that I actually liked. Yeah, because then I have these, yeah, the noise is distorting everything, and yeah, I just don't like it. So that's it from my side alone.
Fair. That's super cool. Seems like your journey has been mainly computational, which is also super valid. And I see that you have been playing with the textures, which is super interesting. I guess the next step would be kind of trying to see if you, for I don't know, I'm imagining if you were taking this like as a real life project, I guess would be, okay, how, with what material do I reproduce this? Like which material is going to allow me to get this either hydrophilic and hydrophobic surfaces and reproduce this phenomenon, right? And I think that erosion simulation might be able to help you figure out where water would collect, which I guess would have to be your hydrophilic surface. So yeah, there's a lot of information from what you have been working on that could inform the next steps of the process. So I think, yeah, it's cool. It seems like you have been having fun with Houdini, which is the purpose of the whole thing. You know, if you get to adopt a little bit any of these tools and have fun with them, then great. That's the true purpose of the thing. So yeah, cool work.
Yeah, great. But I really appreciate the idea that you suggested another meeting maybe next week. Because we randomly decided on the site, and I already have like another idea, and I would be grateful if we could arrange that next week.
Yeah, for sure. I'm not sure if everybody is on the Telegram chat. We can try to set a date and a time on the chat or by email. You guys have our social media. So yeah, just reach out. We can, whoever wants to, we can organize like a meeting to just talk about the processes without, you know, the version of a tutorial or anything, and with enough air so you guys can work freely. And yeah. Thank you for sharing your work.
Yes.
It's super cool.
Thank you.
Yeah.
But also the fabrication process would be also interesting, and yeah, I just wanna I trained a bit with height field, so I feel more confident. But
yeah, I think
I
like
wanna
if
try
I
out
were
more.
if I were to really do it, I would try to just print it with the regular 3D printers on PLA, and maybe put it somewhere that it's subjected to moisture, and see if maybe from the sole texture of the PLA 3D printing, which is like kind of bumpy, and with the right geometry, maybe you can get some results. And if not, then that's okay. You move on to the next material. But I would definitely try it. Like, you had nothing to lose, right? Like,
Great, thank you.
Yeah. Carlos, I think this is an overall great project idea, and that you wanted to introduce hydrophilic and hydrophobic materials inspired by beetles, desert beetles. And then the idea has developed, the Kenneth's idea of generally, brainstorming ideas of like having multiple tools and thinking of the time as not as of our lifetime, but maybe like 5 generation, and thinking of how can we moist the soil, keep it moist. I think it's very, very valid idea. It could be, perhaps applied in Kazakhstan because we both are from here.
Yeah.
It's easily
But
applicable.
actually, now rethinking like remoisturing the soil is a huge thing for me. And I've been thinking about the capillary system. Like instead of this, I tried that, but maybe even using a pattern, but implement like a capillary system that goes like roots under the soil, so that the water that is catched is like distributed through this network and it's not aggressively dumped into one place. Yeah, I don't know. Yeah,
That would be interesting.
let's
Yeah.
see how it develops.
That's a great idea.
yeah, that sounds
That's a
interesting.
cool one. Yeah.
Yeah.
Cool.
Thank you
Okay,
for the feedback.
thank you for showing us your work.
Mhm.
And I think somebody's volunteering, or not really. Anybody else want to show another piece of work?
Hello, hi.
Hey.
Hope you're well. So my group and I, group 6, we were sitting with Donna and Edward, and they were like helping guide us in terms of how to implement our like idea. And so we'll just go ahead and show the Miro board. Just a second. Can you see the board?
It's loading. Yes, we can see it. Perfect.
Yeah, so our site was the Marmara Sea in Istanbul, and we found that there was a lot of mucilage and microalgae in the site. And so when we were trying to, think of the different species that would eat it, and I mean to consume the sea snot, we were thinking of kind of looking at like porous, porous material, and where algae can like foster and grow on it and like attach to it. And so on Houdini, Donna and Edward had gonna guide us through the process of of how to create this panel. So we just did like a quick concept idea of how we wanted to create this dock that would, where the cladding of it would be this like wall or material, where like there would be like the perforations that would occupy these oysters or clams that would be able to consume the sea snots in the area. And today I was going in the area and like physically trying to see all the different like organisms that were in the area, the algae, the like different clams as well, I mean mussels, and just kind of like trying to navigate what's kind of best way we could make it functional in a sense. So this is a very like quick concept like Photoshop, but just wanted to get your ideas and thoughts and your feedback.
I love the image. Like it looks super sci-fi, which I think is like the right kind of look. Yeah, I think this is an evolution of the idea that we had discussed yesterday about maybe how to deal with the cis-knot through geometry, and yeah, I think it's super interesting. Definitely the right way. You have been, or whoever has been working on the model, I think they have been having fun with Houdini, which is also the purpose. I guess the only thing that I would mention, maybe the next step would be how to integrate a little bit better the pier structure with the structure that seems to be aiming to filter out the cis-knot, because right now what I can see is this almost like coral reef geometry is very alien, very sci-fi, very cool, very coral reef as well. And then on top of it, a pier, like a pier, like we all know it, like, yeah, wood, it's steel corners, very clean, very aseptic, right? So how do I, maybe I want to see that difference, but how do I maybe make that transition between those two? Or maybe the pier can also be of a material that's a little bit less, I don't know, less standardized. I think there are many avenues. Or maybe you do like that they look that different, and you can enhance that difference. Maybe you can put a guardrail that looks, very minimalistic, to be like, oh, the clean part is where the humans touch, and the more bio ID part is the cis-knot. You can also enhance that difference if it's something that you prefer. But yeah, I think it's looking super cool.
Yeah, I think you guys did a good job of like going through the bio process, because like you even did site analysis and visited the location, which is super fun.
Yeah,
I'd add,
I was trying to
go for it.
gather all the algae, and I was like opening them up and like trying to, just try to see and inspect them, and but yeah, yeah, thank you. I think like you said, like it's very interesting the way that you like you said that like maybe the material of the like the dock could be something of a biomaterial maybe. I'm just not sure what would like sustain in water and also be something that humans can occupy. So maybe if you guys can guide us on, because we were thinking of using, I think, calcium carbonate as a way to kind of, because it is something that works with water and kind of like limestone. So maybe if that sense, like instead of like the wood and like the steel and everything, it would be in, like more of a something that meshes with the landscape.
Yeah, well,
Yeah,
wood
oyster shell also
technically,
works.
well, wood technically is a biomaterial. Maybe I would try to use it in a slightly different. Maybe I wouldn't use the steel corners. Maybe I would put like I don't know, some kind of interface or some kind of transition between these reefs and the wood. Or I think Edward was talking about calcium carbonate. That's a good option as well. Like, sorry, I cut you off there.
No, you're fine. Just you can do composites with like oyster shell and sand and just as the base, and the binding agents are the more difficult part of biomaterials because they're very water soluble. So if you even do a mix with if it you want to try to avoid it, but if you do cement mixed and reduced down by oyster shells and sand, then it becomes a better material than a wasteful one. But that's just kind of like a halfway solution. Um, yeah. I was also thinking about uh, how you can do simulations to kind of learn about maybe water flow, and like if you did a CFD analysis on the openings and the porosity of it, maybe you can see if it's maybe needs more openings or more closures, just to see if it's like And again, just to add another iterative process to the design and just as a suggestion.
But
Um,
if we were doing it, sorry, I was just a question. But if we
yeah,
were
of course.
doing it in CFD, do we like create like the panel vertically and then allow water to go through the holes?
Mhm.
Mm, No, I think you would want it to be in the same position that it is gonna be on the sea. So if we're talking about, waves going against it, just put it as it would be on the side. You're not gonna be able to analyze the whole pier, so you're probably gonna just take a small chunk of it and start with those analysis, just small scale, see if the holes are doing what you are assuming they are doing, which I would presume would be if the water is actually going through the holes, because maybe the geometry is just pushing the water out and most of it is just being diverted. So you want to run the simulation to see if the water is actually going through more than over, right? Those kind of things. Yeah, just simplify your model as much as possible because the simulation otherwise is going to be too heavy and it's not going to run.
Okay. Thank you
I
so
have a question to add regarding your project, Muhammad. If they're using height filters, tide pools that they showed you, do you think they need to run a partial, like a part of it, or they can run just simplify it and run the whole tide pool landscape that they have
You're
created?
saying run the CFD?
Mm-hmm.
Yeah, so
What would be your strategy?
I would remodel a part of it and just run up to the height of the water. Like anything that like I would try to decrease it as much as possible to the confined space of the water interaction and assumed height and try to keep it as simple as possible. So I would remodel it and probably
Mm-hmm.
just like a few of the openings and a few of the pieces and then try to scale it up from there under that context.
Okay, so like a
Yep.
close-up, right? Like a close-up section of it just to show how the water is flowing through one of the holes maybe and things like that, like more of a
You can do a few of the holes. Try to maybe do one panel or like half panel or section, just so that it's like a little bit more descriptive. Like if you do 2 or 3 holes and like or 3 to 5 holes, like kind of stacked the way that you'd imagine it's going to be, um, it would be better evidence than simply showing like a single hole.
Okay.
Mhm.
And for can we import the Houdini model onto the CFD or would it like clash if we were trying to do the simulation?
No, so you need the CFD reads IGS or SAT files. So the best workflow is to export the geometry from Houdini into Rhino as an OBJ,
Mm-hmm.
and then export from Rhino as an IGS or SAT. Because,
Okay.
but the middle step should be when you export it from Houdini into Rhino, uh, try to quad remesh and reduce it a lot. Maybe you do it poly reduce first in Houdini, or which works better in my opinion is try to copy it by remodeling it in Rhino because Rhino will make very simple polysurface forms that will read much better in CFD than if you tried to work with a Houdini model and reduced it.
Okay, so just like Boolean difference the holes, right? And Rhino, and then just to kind of make the preparations.
Yeah, if you have Rhino 7, then try to
Mm-hmm.
use sub D if you want to keep it smooth.
Okay. Yeah, I do have Rhino 7, so I'll try the sub D. Is there like a specific sub D tool that you suggest?
You can keep it simple in sub D. So just make a box object, and then if you do the shift and control click, you can click planes, and then just simply delete those planes out. And there's
Mm-hmm.
another command. If you go to the sub D bar, there's a closed circle or close loop command. And if you select that one with the loops selected, it'll just close around it. and you'll
Mhm.
have an opening quite easily.
Okay,
You can
perfect.
also find a lot of tutorials on sub-D modeling on YouTube. There are even some 5 to 10 minutes one real quick that just give you the initial tools, and those are gonna also help a bunch.
Okay, thank you guys so much. I really appreciate it, and it was very helpful advice and guidance. Like our group was a bit lost in the beginning, but with like Donna and Edward and all of you, like with your guidance, it helped come through a little bit more. So thank you.
Yes,
Of
absolutely.
course.
Thank you so much. Anyone else? Does anyone else want to present? Thank you, Bano.
I think,
Hey,
Laszlo just turned on his, okay,
Hey,
go for it, man.
Laszlo.
we are shy, but I can quickly just to thank you also, but also to, I don't know, you deserve to, I don't know, to have some results or something like that.
It's
I
okay.
will share my yeah.
Cool.
Oh, no, not this one. So yeah, we started on the first day with river floodings, but then we really tried to focus on the micro and biology, like smaller scale of floodings, because which could be more mitigated with like these subtle biological spots. And we turned to urban flooding, but not obviously when the water is already like accumulated, but when it reaches like the primary surfaces, like the roofs and the higher parts of the cities. So I don't know how local or global this problem is, but I live in Lisbon and it's really hilly. But on the other hand, it's the city is not permeable. Even these cobblestones, they are implemented in cement so that nobody can lift it and throw it to each other. And recently there are huge floodings, and but also it's like it has like the summers are super dry and without any rain for months. So we got inspired by this poikilohydrous species, which they can kind of like hibernate when they don't receive water. And we just wanted to basically create a similar product, but for roof tiles, let's say. And then we made some like initial 3D models, which like basically the strongest concept, or like the strongest element of the concept, is like creating like these plates, or like these pools to collect water. And I think this is like it can be visible on the it can be viewed on this product model. But also I would like to just like we got lost in the computational part a bit, but some initial concept was to also make it like try to make it like multiple layers, so that there are some like the first layer is kind of like shading the layers below, so it's more like a cave, also on almost like a cave system. And also the upper layer, like the water will hit it first, and then it's going to lose energy, and then when it flows to the bottom, like the caves, then it's not disturbing the like the freshly growing life there. So it's a protected cave. And then also, I mean, maybe that's already too, it would be too nice. So if this like verticality could also behave like as a forest model, that like maybe some plants can already grow into these parts, and then they kind of distribute like nutritions to the lower levels of the like as like tree canopies photosynthesize, and then they kind of send down nutritions to the bushes and to the grasses and in a forest. So but that's more like, yeah, more like of a, like it needs more research, like what is the connection between the two layers? What if is it, can mycelium grow into like this if the material is porous enough as a link between, or yeah, like what is the material? Is it, how do we, like regardless of the fabrication, of course, how do we create like a porous material which then on the bottom it's at least on the bottom it's watertight, like it's impermeable. It can be probably some, like the Urban Reef project is an inspiration for us, or Urban Reef, I think that was the name. And but I can also, so maybe it's just me, but I'm not always buying these 3D printing like fabrication methods, but I would love to experiment if there could be like something growing into these caves as a negative of the final. So then we invert it, and then we maybe burn it, like burn the caves, and then we receive the the positive of the initially so we design the spaces and then we invert it. Yeah, so but these are just thoughts. But we got really inspired, and we are, yeah, I'm really happy, and I think the team is really happy that we could take part, and it's really showed us every step of a from concept to product. So kind of we feel energized to do something. But yeah, thank you for.
Laszlo, thank you so much for sharing your work. First of all, I see one thing that is very easy to fix in the solar radiation simulations, but I can see that you didn't get consistent results. And that's something that also happened to me. I should have mentioned it when I was doing the tutorial, but simulations, Caramba, Ladybug, those kind of simulations, in general, they don't like thin surfaces. They like solids. And I presume that this geometry that you analyzed is doesn't have thickness. Is that the case?
I think so, yeah.
So what's happening is that you are getting the results on the top part, but the results of the bottom part, which are basically blue because the bottom part is not getting any sun, since they don't have thickness, they're collapsing into each other. So we're seeing the blue from the bottom part. It's not allowing you to see the results from the top part.
Yeah.
So if you run the simulation again with some thickness, it's going to give you the results that you need. And yeah, it's
makes sense.
You can calibrate your legend. So you know the process. That was just the thing to fix. But other than that, I love the project. I think it's super interesting. I would try to produce some of these roof tiles and leave them out there, and I would see what happens. You know, I wouldn't be surprised if moss starts to grow on them, and maybe some birds start building their nests in there. So I could see it as like a bioreceptive structure of many levels. You know, moss, maybe some small animals, maybe some squirrels, and you could if this is like the prototype, but maybe depending on the orientation of the roof and according to the solar simulation, you can slightly modify the shape of each iteration of these tiles depending on the orientation of the building. If you want to enhance the growth of, maybe these tiles are more adept for moss, maybe these tiles are more adept for small rodents and small birds. And since the more shape of these tiles is quite complex, I would imagine that they are more expensive than the regular tiles, but I wouldn't put them on the whole roof. I would be like, you know what, 20% of my roof is going to be these beautiful, more complex bioreceptive tiles, because I want a patch of my roof to be kind of green and with birds and shit like that, you know? Even thinking a little bit further, if I were you, I would try to, if I and in my group agreed to develop this product further, I would try to test it out there, see if it enhances biodiversity in any way, and then knock on the door of the government and be like, hey, I have this product to enhance biodiversity in urban environments in Lisbon, and I have the numbers to show you that it enhances, you know, animal life in the city. And I want it to be law that 5% of every roof needs to have my tiles for biodiversity process, you know? I can see that as like, if I were mayor of Lisbon, I would give you money to build this thing, man. Like, I think it's a really cool idea.
Thanks.
Yeah, I think it's
Thank you so
interesting
much.
that, like, it's interesting you guys went for roof tiles, because it's something that like people don't necessarily mess with, the roof systems. I think there's some like intrigue there, especially in urban environments, and like the like patterns and like the ways that they'll grow, it'll become super interesting. And it's like, I wonder how you can like show that, you know, like, because people are not going to be able to see it that often, and it's like part of the biodesign is kind of flexing a little bit and being like, you know, look how cool this looks, look how beautiful it is. So maybe it can like transition into a wall system at some point, or maybe like it's only for highly sloped roofs, or you know, the way you handle those conditions.
No, in Lisbon, you see the roofs, actually. It's one of the cities where you really see the roofs because yeah, it's just the topography.
Cool. Then yeah, that's perfect. Then people will be able to kind
Everybody's
of see
hanging
it.
out on like these viewpoints like this we call Mirador.
Mhm.
Makes sense then, yeah.
Yeah.
Yeah, and
I
these are
just have
super
one thing.
fabricatable.
Yeah, two things to add. Maybe perhaps I agree with my colleagues, incredible project. Maybe you could use slip casting as a more affordable and easier to manufacture and scale up fabrication method. And another one is more of a PR idea. And there was an incredible project in the Netherlands called Knock Out the Tiles, or Green Netherlands, I guess. So they encouraged Dutch citizens to knock out the tiles. And if you knock out the tiles and you green your garden or your communal spaces, they would provide you with the instruments and the, you know, seeds and everything else. And cities would compete. And the goal of the country was to be green each year 2% or 1%. And it's happening. It's a movement. It's a very community-based movement. And the men who love football in the Netherlands, when they go to the football and if they bring a tile that they knocked out, they can get a field from the football field, a piece of grass. So this is like a really cool, very interactive, process campaign. I think we could also learn in the biodesign industry few things from you know, PR and marketing.
Definitely.
Yes, great.
But yeah, thanks, Laszlo.
Thank
Great
you so much.
It's a great idea.
I think we have a last group. Group number 4.
Yes. Hi everyone.
Hi.
Wait, let me see.
Hello.
We don't see you, by the way.
Oh,
Guys, before this group gets started, I have to leave. I have a meeting at work.
Me too.
I'm gonna leave you here, but thank you guys for participating. Thank you to Dana Network for saving me in this endeavor. And yeah, just keep in
Yeah.
touch, and well, I'll talk to you guys soon.
Yeah.
Cool. I'm gonna give you host powers, Edward, so you guys can keep the call alive. Okay. Bye, guys.
Bye,
see you.
Ken.
Can you see my screen?
Yes.
Yes.
Okay. Yeah. So, I'm representing room number 4. This is like a very conceptual phase. We didn't get to dive into the modeling and simulation yet. I think we are, yeah. So, I think this is gonna be quick. For the site, we chose Madagascar as a site, and our main issue is we are looking into 2 main issues, which is the social and environmental impact of the mining in this area of Madagascar. So from the left, it's like in the southeast of Madagascar, and as we can see here, the mining site is like right in the middle of the zoomed in image, and the problem is there was some sort of leak from the mining waste. So I think the water has been polluted, and it has impacted the local community, and which is the majority are like fishermen, and so that caused a lot of a major environmental problem. Like the fish are being just dead, and which the economic impact is, of course, like the fishermen, they don't have income, but also the water became more acidic, and these fishermen, their wives are mostly like weavers, so plants that they need for their weaving, like weaving baskets and all of these crafts, they don't grow anymore, so they have to kind of import or order it from another area. So that's our main issue for this project. This diagram is summarizing our design process. A lot of research has been done here. So we would like to fit I don't know if we can say like the solution or the design to the local context. So I think that's also why we are still in this phase. So to address this social and environmental problem, we went into searching what type of plant can we use that's already available, but also can perform the function of filtration or filtering the water from the upstream from the mining site, and that requires an understanding of how the water flow. So we had to do some research, and what's mostly available there is the mangroves, which has like a root system that's amazingly performative in regards of filtration. So, and there is also algae that can be found in the area, and we thought about like, what would be our solution that can regenerate the economy, not only the environment, but also the economy in the area. So everyone can benefit from it, but not only like the living or not only the biodiversity, the marine biodiversity, but also the people. So that's kind of how we process, how we proceed for this project. And with all of this information, with all this research, the context, we came with these two concepts that we are still developing. Hopefully we get to touch base with the team. So the first one is like some sort of walkable structure, which is inspired from this project by RISD students and researcher, having the routing system that's kind of help to filter the water, and there is the material for the weaving kind of, it's not submerged. So how we are trying to get something like that, like on the edge of this walkable structure, but also how can we incorporate that idea with something that will benefit from the algae? So the idea would be like 3D print the structure that will host the plant, and from local algae, this is there are like 2 videos and reference that explain it more, like, or that we used as reference here. So that's the first concept. It's supposed to be something that's walkable, interactive, people can enjoy. The second one would be using a framework. I'm not sure if you're familiar with Terraform One project. They use the type of framework to grow the material for the structure. So since mangroves are like very it's present in the area, the idea would be like, how can we develop a framework that will kind of have this design intent that we would like to have this aesthetic that we are trying to achieve. So that type of framework would be the one we are trying to develop instead of playing with the material. So how can we guide the mangrove to get this look, aesthetics of something computational, generative, but also perform the function that we are aiming to, which is filtration and balancing the pH of the water. So that's sort of where we are at right now. It's very conceptual. We are not at the simulation phase yet, but yeah, that's what we have.
Cool. It's a interesting idea, and I think you can probably utilize both together into one project if you had a big enough team. I think like having the filtration tiles is an interesting concept, I think. And it's very easy to also think about the ways that you can do the analysis for them, because just having like water flow analysis or wind flow for the guided mangroves could be very informing. The for the concept of the acidity, I think it's good to look into local species that and organisms that would help support that, because maybe they could be supported through something implemented in the tiles. And that would be helpful to kind of encourage the regulating of the environment. So yeah, I think cool stuff. You guys did a good job. I like the overall kind of consideration and process. And yeah, Donna, you want to add anything?
Same, yeah. I love how considerate the project is to location, environmental, socio-economic, and biodiversity. So it's a really beautiful project. Loved your AI renderings. Yeah, I think this has a great potential and avenue to explore. We would love to get in touch with you guys if you're interested sometime maybe next week to have a quick call if you'd like to work on this project further.
I think that would be great.
Yeah.
Yeah. Just
it will be more free as well.
An interesting point that Donna made was the socioeconomic, because in a way we all have to kind of sell these ideas. So it's good that you're kind of considering how to be effective for the community as well.
Yeah.
Awesome. Thank you.
Yeah, thank you.
Okay, I guess this is a wrap, right?
Unless we have one more.
I think we are the last one.
Okay.
I just need to head out now. Sorry,
Yeah,
guys.
I can wrap it up, Donna. That's cool.
Yeah, okay, great. Great experience. Thank you everyone for joining. And thank you, Kenneth, Ed, for being partners in crime. So yeah, I'll see you guys next week, I guess, then.
Yeah.
Bye.
Thank you so much. Bye-bye.
Okay. Can you hear me?
Yep, show me what you got.
I'm Masoud from room 1. I'm gonna walk through our work. We selected Hormuz Island as our site. Hormuz Island is in the south of Iran, where Persian Gulf meets the Oman Gulf. In the Hormuz Strait, it's a beautiful place with a colorful beach and colorful soil. But there's some issues. The Hormuz Strait is also where all the oil, a large part of the oil production of the world passes through, and exploration, extraction, and transportation of it creates some pollutions. It is harming the species that live there. To solve to propose a solution for this problem, that the water is polluted, we inspired from coral reefs and how the shape of them can help the organisms and different kind of species grow. We tried to create some. We tried to create some somehow organic forms and implement some patterns on them. That these patterns can possibly be well habitat for these microorganisms like planktons and other nutrients stick to these patterns and make a good place for the other organisms to grow. So this how we could maybe purify the local water and create a better place for the for that species to grow and don't face extinction. That's it.
Cool. No, it's good to actually have a straightforward approach, and this is one of those. And I think it's good to see that you guys had organisms that you got a basis and concept off of and found forms off of that, because they naturally would inform the process. For the oil, I'm assuming there is a lot of residual oil in the liquid in the water. Yes or no? Yeah, so in that case, what's good is to do research if you haven't already on what organisms that are local to that environment that are best at reducing it or can adapt to that environment well, and then either find processes that encourage that growth or design ways that they do it that you can do it in your own version, your own way. So the filtration and the cleansing can be kind of encouraged, and then through that it'll encourage more growth. I like these units that you created. They seem pretty fabricatable, and they're something that you can actually similar to the roof tiles. You can just have it made, throw it on site, and come back in a week and just check the data and see how much has actually occurred onto it. So this is something that you're at a phase where you can take the next level and start testing it and seeing if it's working. The real life analysis is sometimes more effective than the computation one because it's literally what's going on. So this is the case where you can handle it like that. And it'll also inform the next iteration because you'll see where maybe some areas are not going growth or maybe it's not doing anything. And you'll learn from that process. That's cool. Good job.
Thank you.
Mm-hmm.
I maybe also want to add that there's an other island near that named Kish Island, which has coral reefs, and the water around that is really pure, and you can see through that in maybe into the depth of the sea on that part. And I think that those kind of species can also grow in this location.
Good. Yeah, so you have precedent. You have something that you can see if it will work in that local environment. It's good research. I think also it's good to research if the species, like maybe there needs to be some preliminary cleansing before you introduce them because maybe it's too problematic, or sometimes it might require in this situation multiple types of cleansing. Or another way to think about it also is in stages. So maybe step one is to introduce this species or this solution, and step two is to introduce the now organism into your new panel, and then it'll grow because it's stage one has been completed.
All right. Thank you.
Thank you. Cool. So we're gonna wrap it up. Thank you guys, the ones that are left, the stragglers. It's been fun. We can reach out for those who want to do some more in the future. Maybe in a week or so, we'll see what's going on. We'll keep the mural board open, and of course, the Telegram is going to stay open as well. So just stay in touch, and I hope you guys had fun. We really enjoyed kind of showing us everything that we had learned and the things that we found were valuable. And it was nice to see that everyone else thought it was important information too. So appreciate you all, and we hope that you guys have a good weekend. See you guys.